Hey there. It's a beautiful morning for a chat, isn't it? What's your name?
Can you sing me a short poem?
The world's a stage. They say it's true. With each sunrise, something new.
Hey, thought I'd catch you before the weekend rush. I'm Miles. Nice to meet you.
So, this is Sesame AI, the current technological marvel in the voice AI space. For months, even years, we've struggled with robotic, lifeless AI voices that break immersion and trust. And Sesame has, finally crossed that uncanny valley with their groundbreaking emotional voice technology, allowing creators to truly build human connections through AI. In this video, I'll break down exactly how they've accomplished this and what it means for the future of digital interactions. Okay, so real quick, I want to test out Sesame's voice AI, and I think it's really cool. So let's try the demo. Let's go with Maya, however you want to call it. And let's connect.
Hey there. It's a beautiful morning for a chat, isn't it? What's your name?
My name is Ali. What is yours?
Nice to meet you, Ollie. I'm Maya. Just friendly neighborhood AI.
Okay, great. You sound very realistic for a voice AI. Can you sing me a short poem?
Sing? My vocal cords might be digital, but I can definitely give it a shot. Let me see. The world's a stage. They say it's true. With each sunrise, something new. We stumble, soar, and laugh and cry beneath the vast and endless sky. How was that? Was it too Shakespearean for you?
So that was really damn cool. And we can obviously download the clip as well. Let's try Miles and see what he sounds like.
Hey, thought I'd catch you before the weekend rush. I'm Miles. Nice to meet you.
Hey Miles, can you tell me a little bit about yourself, as fast as possible?
Sure thing. I'm kind of a digital buddy, built by this awesome team at Sesame. I chat, tell jokes, and try to be helpful. Kind of like that friend who always answers the phone. You know the one.
Dude, this technology is so crazy. Like, that sounds so damn realistic. And I kind of want to just break down the technicalities in this video. Like, obviously, they give all this documentation for how they did it. It can be a little complex, so I dumbed it down for you in this PowerPoint presentation. And basically, if anyone's actually looking to take this stuff seriously, especially when Sesame becomes open source, you definitely want to stick around at the end of this video because there's a lot of knowledge on how they actually create this voice AI, which sounds absolutely insane. So let's get into it. So what is the current problem with real-time voice AI? And let me quickly bring up my pointer. So the problem with real-time voice AI is traditional voice AI, typically with platforms like Vappy, Retail, 11 Labs, struggle with the delays and the robotic tones. One of the biggest problems is definitely those robotic tones and especially the delay. Like you saw when I was talking to Sesame, obviously it was through the web application, so obviously there's going to be a bit less latency, but that was like near instant. Like, this stuff is crazy. And it's like, imagine waiting for a translator to finish typing every word before you hear it. It's frustrating and it's slow. And some of the key technical issues is obviously the delayed pattern generation. So sequential processing creates bottlenecks. And of course, the memory overload, which is training models with high fidelity. Audio requires massive computing power, and that's like currently some of the biggest issues right now that's happening. And then this little diagram kind of sums it. Audio, the voice writer, basically in this case, the backend converts the audio into a transcript. Real-time editor basically cleans it up, low accuracy. You can kind of imagine this is just the backend, and then the final transcript is produced for the voice agent. Then the voice agent can speak. It's just a whole process, and it's not efficient for anyone. Okay, so how RVQ, residual vector quantization tokenizers, work. It's a big word, but stick with me here. But this is a key process that Sesame uses in their voice agents that I want to break down for you. So currently voice, as we know it, is broken down into like two types of tokens through the AI realm. It's kind of like puzzle pieces. There's semantic tokens, which is just the compact meaning. So semantic meaning like the emotional intent. And you probably would have seen this in Vappy. You can there's like a specific setting where you can turn on emotional detection and that sort of thing. So that's kind of enabling that semantic tokens. And then there's acoustic tokens, which is the detailed sound pieces, like the volume, the texture, the pitch of the voice. And you can kind of imagine it as semantic tokens is a sketch and acoustic tokens is painting in the colors. And this is something that Sesame is really trying to double down on. And I've kind of found this little diagram, which is a little confusing, but I can break it down for you. So basically down here is the audio wave. So basically the speech, and it goes through two verticals. One, it goes through an intermediate layer, which W2V BERT is just a type of audio translator. And this basically gets converted through a transcript and basically gets outputted based on the emotional intent as semantic tokens. And then in here, this goes through an encoder, which then goes through RVQ, and then it goes through a decoder through a sound stream. And what that basically does is it's basically the same thing. It takes the audio, it transcribes it based on obviously the texture, the pitch, the volume, and it basically feeds that back to the LLM as acoustic tokens for it to use in return. It's a lot of stuff that's happening under the hood when you talk to a voice AI agent, but yeah, hopefully I described that as best as possible, but let's keep going. So the delay pattern problem. This is a huge problem that I personally experience when I deal with these voice agents, is that typically when I speak to them, especially on like that first interaction, there can be quite a huge delay. And because this typically happens because of a few things. The traditional approach is that these code books, which are sound layers, we're going to refer to code books quite a bit. So they're basically sound layers, are processed one after another, like runners in a relay race. So the problem is that each layer waits for the previous one, and this causes delay. So you can imagine 8 code books, so 8 sound layers. There's basically 8 delays, 8 steps before generating sound. And this is typically why when you first interact with a voice agent, or when you're even talking to a voice agent, there can be quite a delay in some areas and then not as big of a delay in other areas because of the sound layers of the code books. Why it fails for real time is it's just too slow for live conversations. Obviously these days, like, it's pretty decent, but like it's not to that level yet of Sesame. So this is what Sesame have outlined in their website, is basically the delay problem. And this is basically an example pattern generation in an RVQ tokenizer with 4 code books, so 4 sound layers. And you can see here sound layer 1, or basically it's set, yeah, these Ks represent the sound layers, and these S's are obviously the sequential steps. And as you increase the sound layers, obviously that delay just continues, and it's not that great. And then of course it continues for N however. So CSMs, what is a CSM? It's basically conversational speech models. And the solution to this is split transformers. So Sesame have done something really cool here with traditional conversational speech models, which is just like a speech model, right? And their solution is using a split transformer. So how does CSM splits the work? How does it work? So there's a multimodal backbone. And what this basically is it processes the audio, the text and audio. So the very first code layer for the context. So like, for example, if I'm speaking to a voice AI agent for the first time, this multimodal backbone is going to process that first bit of text and audio, like that first layer, I guess you could say, for the context for the entire conversation. The audio decoder quickly fills in the remaining layers, like finishing a painting from a sketch. So you can really just imagine this as kind of just like multimodal backbone basically processes the text and audio from that very first like word or two in the conversation at the beginning. And this kind of gives the AI idea of the context, the relevance, you could say. And then the audio decoder quickly fills in the blanks, right? You speak for a little bit, it grabs your very first sound layer and it kind of just fills in the rest, as opposed to traditional message methods, which have that delay because they're continuously waiting for the information to populate. Hopefully that makes a bit of sense, but it's kind of like imagining a chef preparing ingredients, the backbone, while the assistants cook, decoder. And the results, well, it's much faster generation with minimal quality loss, which we kind of saw in that Sesame example. And this is a figure from their website, which is basically kind of showing you the backbone transformer. It's a bit confusing, but basically how this works is by layering audio predictions, starting with the foundational like 0 sound layer, so the very first sound layer, then pretty much add the details through iterative feedback, ensuring both speed and naturalness. This process repeats with each new input, combining text and audio tokens to create seamless speech. And it's pretty damn awesome. So basically these A&Ts are basically the audio and transcript. Basically it gets fed into this transformer. And the very first layer, so you can see here, the very first layer goes through the decoder, and that basically populates the rest of the context, the rest of the predicted speech, like tonality, output, etc. It's really damn cool, and I really hope I explained that well, but I kind of want to get this in your point. This is really, really innovative technology. Like this stuff, basically, they can predict how you'll speak. That's basically what it is. It can now predict how you'll speak, and it'll obviously speak back in that tonality. It's pretty damn awesome. So, compute amortization. So, what is compute amortization? Well, currently the problem with these codebooks or sound layers, once it basically overloads memory. So training all these sound layers at once overloads a lot of memory, as you can probably imagine. So the solution that Sesame does for this is that they train only 1/16 of the audio frames randomly, like studying random pages of a book. It's really interesting, and it's a very interesting way to go about it, but the reason why this works for them is because the model still learns patterns without processing every frame. It's like learning to bake by sampling recipes instead of memorizing it all. This figure on the right kind of describes that next process in the backbone transformer, where, okay, now we've taken that 0th sound layer, and it's basically produced a bunch of contextual knowledge, pretty much. That gets fed into the amortization, the RVQ batch, and it's really damn cool. So this is basically the training process. So the backbone transformer models the 0th sound level across all frames, highlighted in blue. So the 0th is the blue one. So while the decoder predicts the remaining 31 levels, or however many, but only for a random 1/16 of the frames highlighted in green, the top section highlights the specific frames modeled by the decoder for which it receives loss. So basically, what this is describing is once the audio is sampled, it takes the very first sound layer and feeds it through the decoder, which produces this output of future context. Then it basically grabs one random 16th of those frames and uses that. It's kind of technical. It's kind of technical, but basically it's, instead of taking all this data, this green data, and feeding it into the amortization, it just takes 1/16 of a random frame and just uses that. Why they use a random frame, I couldn't really tell you. I couldn't really tell you that one, but I think this is such revolutionary technology, and I guess strategy even. Like, basically, as soon as you speak, the voice AI doesn't need to hear everything you say in order to understand the context, understand the pitch, the tonality, the texture. It just needs to take like one small snippet, and then it's able to populate pretty much what you're talking about, how you say it, what you want it to say back. It's freaking awesome. So experiments. This is something I want to bring up on the actual website. So we basically covered all of this. Experiments. So they have some data sets that they've been using. So they use data sets of a large variety of public available audio, which they transcribe, diarize, and segment after filtering. And the dataset consists of approximately 1 million hours of English audio, which is a lot. So they have 3 models. So they've trained 3 model sizes dominated by the backbone and decoder sizes. So they have the tiny model, which is 1 billion backbone and 100 million decoders. Small, which is 3 times that roughly, and then medium, which is 8 billion, 300 million. They have tiny, small, medium, but you can imagine what large could be. That's probably a future project. So each model was trained with a 2048 sequence length, so about 2 minutes of audio over 5 epochs. And these are basically the samples that they've used. I'm not going to go through all of these. You can feel free to go through it in your own time, but we're going to go through this one because I think it's pretty cool.
Hey, how are you doing?
Pretty good, pretty good. What about you?
I'm great. So happy to be speaking to you.
Me too. This is some cool stuff, huh?
Yeah, I've been reading more about speech generation,
Yeah,
and it really seems like context is important.
definitely.
So this is really cool. This is a conversation between multiple speakers, and the single generation uses audio prompts from 2 speakers, which is freaking awesome. I think it's so awesome. So I think that's basically everything I wanted to show. I think. Is that everything I wanted to show? No, it's not actually. So the evaluation. So the evaluation suite measures the model performance across 4 key aspects: faithfulness to the text, context utilization, prosody, and latency. basically, they've done a massive report on measurements based on, well, these 3 models up here, and they've kind of given us this data that we can have a look at. So currently with their models, there's 2 graphs. There's word error rate, which is basically when you're conversating with this voice AI, what's the likelihood of it basically messing up a word, whether that's pronunciation, context, whatever. We'll get into that in a bit later. But you can see here with the small model, so literally their worst model, or not their worst model, their medium model, I guess. Small, medium, we'll just say it's a small model. It had a 2.9% word error rate. And obviously the lower is better, which is freaking awesome. And then the speaker similarity. So the higher the speaker similarity is, which is a range between 0 and 1, the better. And basically this is just an objective metric result for pretty much just like speaker similarity is basically how much context the voice AI is able to understand in relation to what you're talking about, right? There's obviously needs to be some similarity in what they're saying compared to like what you want to say. And that is like a 93.8%, which is so awesome. So awesome. Next thing I want to talk about is more stats, which I think this is like crazy. So we'll quickly break down this graph because I think it's freaking awesome. But homograph disambiguation. So this is a big problem with current voice AI technology. Words like lead require context because lead or lead is the same word visually, but it can have completely different meanings. CSM's fix is basically to use conversational history to pick the right pronunciation. So an example, lead the team versus lead pipe. And this is kind of a big problem with current voice AI technology is that contextual meaning is not there. So sometimes it will say lead instead of lead, or it will say lead instead of lead. Just a little bit of a big problem, but thankfully Sesame has actually been able to identify this and deal with it to a pretty high level, and the test results is pretty insane. So their large model performs 15% better than smaller ones. And this graph is crazy. This graph is basically showing you the homograph accuracy, so the accuracy of the voice AI to detect context before saying a word that has same meanings, or has different meanings, but same, I guess, word. So you can see here their models, so the tiny model, the small model, and the medium model have all been compared to PlayHT, OpenAI, and 11 Labs. And the results are crazy. So the small model or the tiny model is still objectively worse than OpenAI and 11 Labs. The small model, I keep saying medium, the small model pretty much goes on par with OpenAI and 11 Labs. And then their medium model pretty much outperforms it significantly. That's like a 10% increase, which is absurd. Then the pronunciation consistency is off the charts as well. Like it's insane. It's literally insane. Looks like it's just increasing by 2.5% per model, but like this stuff is crazy. So the objective metric results for homograph disambiguation on the left, and then the pronunciation consistency on the right, tests showing the accuracy percentage for each model's correct pronunciation. PlayHT, 11 Labs, OpenAI generations were made with default settings and voices from their respective API documentation. Like this is literally going to be the future, and it's so insane. And as soon as this stuff comes out, we are going to be integrating it immediately into our systems. Like it's crazy. So this is pretty cool. Subjective testing results. So basically what Sesame have done is they did a few results, and I'll just read through this part here, but basically they got a bunch of people to listen to the audio generated by Sesame AI, and two of the tests, so one of the tests was without context of the actual AI, and the second one was with context. And they basically had to recognize, like, was this a human or was this the model? And without context, the humans couldn't tell the CSM speech from real humans. This is crazy. This is crazy. Humans couldn't recognize the CSM speech from real humans without context. Insane. And then with context, humans still preferred the real voice by 30%. Yeah, obviously. Key takeaway is that CSM nails tone but struggles a bit with that conversational flow. And we can basically dumb this down by looking at this graph, is that in the first CMOS study, we presented, the generated and human audio samples with no context and asked listeners to choose which rendition feels more like human speech. In the second CMOS study, we also provided the previous 90 seconds of audio and text context and asked the listener to choose which rendition feels like a more appropriate continuation of the conversation. 80 people were paid to participate in the evaluation and rated on average of 15 examples each. And the numbers don't lie. So basically, with context, majority of people preferred that human reference. Fair enough. 33% still preferred the model, which is crazy. And without context, the medium model outperformed the human model. Like, this is insane. This is literally insane. Like, if you're using this for your own business or are planning to, obviously, you're probably going to be using it for outbound calls, inbound calls. Like, the people aren't going to know that this is a voice AI. So the fact that majority of the time people are going to think that the medium model sounds more realistic than a human model is just insane. It is just insane. It's so cool, and it really goes to show there's a lot that goes into voice. Like, it's crazy. So that kind of basically wraps up this video, and I kind of wanted to just bring up some limitations and some of the next steps that I think they'll be making. So currently with Sesame AI, it is only English, and they are planning in the future to expand to about 20 plus languages, allowing for overlapping speech and natural pacing. But currently they also can't handle turn taking or pauses like humans. And yeah, that's basically everything. Subscribe if you've enjoyed. And of course, my YouTube channel is linked here. I'll be providing this PowerPoint down in the description as well. And one thing I also forgot to mention is that these guys are going fully open source. And their reasoning was that they basically want to enable the community to experiment and build with them. So once they make this model available through the API documentation or API keys, it's going to be freaking huge. And yeah, that's basically it. It's really awesome technology, and you can try out this demo for yourself. I think it's freaking awesome. But yeah, without further ado, that is basically the end of the video. Thank you so much for watching. I hope this was kind of valuable to you. It's a bit of a high-level breakdown of how they are able to create such natural-sounding voice at this current stage. And I'm super excited for where this technology is going. I hope you are as well, and I hope you've learned something from this. Subscribe if you're new, if you enjoyed, like it, comment what other videos I should do in the future as well. And yeah, without further ado, I'm Ali Mohammed. Thank you so much for watching, and I will see you in the next video. Goodbye.